This video is a composite of layered James Webb Space Telescope images, designed to create the illusion of an extreme cosmic zoom. What you're seeing is a recolored, stylized version, not raw data, but my art interpretation. The bright star at the center of NGC 3132, while prominent when viewed by the James Webb Telescope in near-infrared light, plays a supporting role in sculpting the surrounding nebula, changing the shape of this planetary nebula's highly intricate rings by creating turbulence. The pair of stars are locked in a tight orbit, which leads the dimmer star to spray ejected material in a range of directions as they orbit one another, resulting in these jagged rings. Hundreds of straight, brightly lit lines pierce through the rings of gas and dust. These spotlights emanate from the bright star and stream through holes in the nebula like sunlight through gaps in a cloud. But not all of the starlight can escape. The density of the central region, set off in teal, is reflected by how transparent or opaque it is. Areas that are a deeper teal indicate that the gas and dust are denser, and light is unable to break free. This is not only a crisp image of a planetary nebula, it also shows us objects in the vast expanse of space behind it. The transparent red sections of the planetary nebula and all the areas outside it are filled with distant galaxies. The Cartwheel Galaxy, located 500 million light-years away in the Sculptor constellation, is composed of a bright inner ring and an active outer ring. While this outer ring has a lot of star formation, the dusty area in between reveals many stars and star clusters. The mid-infrared light captured reveals fine details about these dusty regions and young stars within the Cartwheel Galaxy, which are rich in hydrocarbons and other chemical compounds, as well as silicate dust, like much of the dust on Earth. Young stars, many of which are present in the bottom right of the outer ring, energize surrounding hydrocarbon dust, causing it to glow orange. On the other hand, the clearly defined dust between the core and the outer ring, which forms the spokes that inspire the galaxy's name, is mostly silicate dust. The smaller spiral galaxy to the upper left of Cartwheel displays much of the same behavior, showing a large amount of star formation. In this mosaic image stretching 340 light-years across, displays the Tarantula Nebula star-forming region in a new light, including tens of thousands of never-before-seen young stars that were previously shrouded in cosmic dust. The most active region appears to sparkle with massive young stars, appearing pale blue. Scattered among them are still embedded stars, appearing red, yet to emerge from the dusty cocoon of the nebula. Young stars still surrounded by dusty material are blowing this bubble, beginning to carve out their own cavity. Astronomers use two of Webb's spectrographs to take a closer look at this region and determine the chemical makeup of the star and its surrounding gas. This spectral information will tell astronomers about the age of the nebula and how many generations of star birth it has seen. Farther from the core region of hot young stars, cooler gas takes on a rust color, telling astronomers that the nebula is rich with complex hydrocarbons. This dense gas is the material that will form future stars. As winds from the massive stars sweep away gas and dust, some of it will pile up and, with gravity's help, form new stars. Pillars of creation. The stars show up in near-infrared light, marking a contribution of Webb's near-infrared camera. Near-infrared light also reveals thousands of newly formed stars. Look for bright orange spheres that lie just outside the dusty pillars. In mid-infrared light, the dust is on full display. The contributions from Webb's mid-infrared instrument are most apparent in the layers of diffuse, orange dust that drape the top of the image, relaxing into a V. The densest regions of dust are cast in deep indigo hues, obscuring our view of the activities inside the dense pillars. Dust also makes up the spire-like pillars. This is one of the reasons why the region is overflowing with stars. Dust is a major ingredient of star formation. When knots of gas and dust with sufficient mass form in the pillars, they begin to collapse under their own gravitational attraction, slowly heat up, and eventually form new stars. Newly formed stars are especially apparent at the edges of the top two pillars. They are practically bursting onto the scene. At the second pillar, undulating detail in red hints at even more embedded stars. These are even younger and are quite active as they form. The lava-like regions capture their periodic ejections. As stars form, they periodically send out supersonic jets that can interact within clouds of material, like these thick pillars of gas and dust. These young stars are estimated to be only a few 100,000 years old, and will continue to form for millions of years. The Pillars of Creation is a small region within the vast Eagle Nebula, which lies 6,500 light-years away, the dwarf galaxy Wolf-Lundmark-Melotte, or WLM. The zoom begins with a ground-based image captured by the European Southern Observatory's Omega CAM on the VLT Survey Telescope. L1527 is a molecular cloud that harbors a protostar. It resides in the constellation Taurus, about 460 light-years from Earth. The more diffuse blue light and the filamentary structures in the image come from organic compounds known as polycyclic aromatic hydrocarbons, PAHs, while the red at the center of this image is an energized, thick layer of gases and dust that surrounds the protostar. The region in between, which shows up in white, is a mixture of PAHs, ionized gas, and other molecules. As the protostar continues to age and release energetic jets, it'll consume, destroy, and push away much of this molecular cloud, and many of the structures we see here will begin to fade. Eventually, once it finishes gathering mass, this impressive display will end, and the star itself will become more apparent, even to our visible light telescopes. This image includes filters representing 7.7 microns light as blue, 12.8 microns light as green, and 18 microns light as red, a growing protostar embedded within a molecular cloud. The center of the image shows a bright, red region, where the growing protostar resides, with a thin, gray lane of matter cutting through it horizontally. A merging galaxy pair cavort in this image captured. This pair of galaxies, known to astronomers as 2ZW96, is roughly 500 million light-years from Earth and lies in the constellation Delphinus, close to the celestial equator. As well as the wild swirl of the merging galaxies, a menagerie of background galaxies are dotted throughout the image. The two galaxies are in the process of merging and as a result have a chaotic, disturbed shape. The bright cores of the two galaxies are connected by bright tendrils of star-forming regions, and the spiral arms of the lower galaxy have been twisted out of shape by the gravitational perturbation of the galaxy merger. It is these star-forming regions that made 2ZW96 such a tempting target for Webb. The galaxy pair is particularly bright at infrared wavelengths thanks to the presence of the star formation. This observation is from a collection of Webb measurements delving into the details of galactic evolution, in particular in nearby luminous infrared galaxies such as 2ZW96. These galaxies, as the name suggests, are particularly bright at infrared wavelengths, with luminosities more than 100 billion times that of the Sun. An international team of astronomers proposed a study of complex galactic ecosystems, including the merging galaxies in 2ZW96, to put Webb through its paces soon after the telescope was commissioned. NGC 346 is a young open cluster of stars with associated nebula located in the Small Magellanic Cloud that appears in the southern constellation of Tucana. It was discovered August 1, 1826 by Scottish astronomer James Dunlop. Dreyer described it as bright, large, very irregular figure, much brighter middle similar to double star, modeled but not resolved. On the outskirts of the cluster is the multiple star system HD 5980, one of the brightest stars in the Small Magellanic Cloud. This cluster is located near the center of the brightest H2 region in the SMC, designated N66. This is positioned in the northeast section of the galactic bar. Stellar surveys have identified 230 massive OB stars in the direction of this cluster. 33 of the cluster members are O-type stars, with 11 of type 6.5 or earlier. The inner 15 PC radius of the cluster appears centrally condensed, while the area outside the volume is more dispersed. The youngest cluster members near the center have ages of less than 2 million years, and observations suggest the cluster is still engaged in high-mass star formation. A crowded field of galaxies throngs this picture of the month from the James Webb Space Telescope, along with bright stars crowned with Webb's signature six-pointed diffraction spikes. The large spiral galaxy at the base of this image is accompanied by a profusion of smaller, more distant galaxies which range from fully fledged spirals to mere bright smudges. It is situated a little over 1 billion light-years from Earth, in the constellation Hercules. One of Webb's principal science goals is to observe distant galaxies in the early universe to understand the details of their formation, evolution, and composition. Webb's keen infrared vision helps the telescope peer back in time, as the light from these distant galaxies is redshifted towards infrared wavelengths. Comparing these systems with galaxies in the local universe will help astronomers understand how galaxies grew to form the structure we see today. Webb will also probe the chemical composition of thousands of galaxies to shed light on how heavy elements were formed and built up as galaxies evolved. To take full advantage of Webb's potential for galaxy archaeology, astronomers and engineers must first calibrate the telescope's instruments and systems. Each of Webb's instruments contains a labyrinthine array of mirrors and other optical elements that redirect and focus starlight gathered by Webb's main mirror. This particular observation was part of the commissioning campaign for Webb's near-infrared imager and slitless spectrograph. As well, Able 2744, nicknamed Pandora's Cluster, is a giant galaxy cluster resulting from the simultaneous pileup of at least 4 separate, smaller galaxy clusters that took place over a span of 350 million years, and is located approximately 4 billion light-years from Earth. The galaxies in the cluster make up less than 5% of its mass. The gas, around 20%, is so hot that it shines only in X-rays. Dark matter makes up around 75% of the cluster's mass. This cluster also shows a radio halo along with several other Able clusters. It has a strong central halo along with an extended tail which could either be relic radiation or an extension of the central halo. Renato Dupke, a member of the team that discovered the cluster, explained the origin of the name in an interview. "We nicknamed it Pandora's Cluster because so many different and strange phenomena were unleashed by the collision. The north and east compass arrows show the orientation of the image on the sky. This observation features the massive galaxy cluster RxJ2129. Due to gravitational lensing, this observation contains 3 different images of the same supernova-hosting galaxy, which you can see in closer detail here. Gravitational lensing occurs when a massive celestial body causes a sufficient curvature of spacetime to bend the path of light traveling past or through it, almost like a vast lens. In this case, the lens is the galaxy cluster RxJ2129, located around 3.2 billion light-years from Earth in the constellation Aquarius. Gravitational lensing can cause background objects to appear strangely distorted, as can be seen by the concentric arcs of light. Astronomers discovered the supernova in the triply lensed background galaxy using observations from the Hubble Space Telescope, and they suspected that they had found a very distant type Ia supernova. These supernovae always produce a fairly consistent luminosity. At the same distance, one looks as bright as any other, which makes them particularly helpful to astronomers. As their distance from Earth is proportional to how dim they appear in the night sky, objects with known brightness can be used as standard candles to measure astronomical distances. The luminous, hot star Wolf-Rayet 124 is prominent at the center of the James Webb Space Telescope's composite image combining near-infrared and mid-infrared wavelengths of light. The star displays the characteristic diffraction spikes of Webb's near-infrared camera, caused by the physical structure of the telescope itself. NIRCam effectively balances the brightness of the star with the fainter gas and dust surrounding it, while Webb's mid-infrared instrument reveals the nebulous structure. Background stars and galaxies populate the field of view and peek through the nebula of gas and dust that has been ejected from the aging massive star to span 10 light-years across space. A history of the star's past episodes of mass loss can be read in the nebulous structure. Rather than smooth shells, the nebula is formed from random, asymmetric ejections. Bright clumps of gas and dust appear like tadpoles swimming toward the star, their tails streaming out behind them, blown back by the stellar wind. streaks of light and bright arcs betray the presence of a vast gravitational lens. A galaxy cluster in the foreground has magnified distant galaxies, warping their shapes and creating the bright smears of light spread throughout this image. This effect, referred to by astronomers as gravitational lensing, occurs when a massive celestial object such as a galaxy cluster causes a sufficient curvature of spacetime for light to be visibly bent around it, as if by a gargantuan lens. One of the consequential effects of gravitational lensing is that it can magnify distant astronomical objects, letting astronomers study objects that would otherwise be too faint or far away. This useful quirk of gravitational lensing has also been used to reveal some of the most distant galaxies humanity has ever encountered. The long, bright, and distorted arc spreading out near the core is one such example. A distant galaxy known as the cosmic seahorse, its brightness is greatly magnified by the gravitational lens, which has enabled astronomers to study star formation there. This image was captured by Webb's primary near-infrared camera and contains the lensing galaxy cluster. It lies at a distance of around 6.3 billion light-years from Earth, in the constellation Coma Berenices. By combining Webb's sensitivity with the magnifying effect of gravitational lensing, astronomers were able to use this gravitational lens to explore the earliest stages of star formation in distant galaxies. A new high-definition image from the James Webb Space Telescope's near-infrared camera unveils intricate details of supernova remnant Cassiopeia A and shows the expanding shell of material slamming into the gas shed by the star before it exploded. The most noticeable colors in Webb's newest image are clumps of bright orange and light pink that make up the inner shell of the supernova remnant. These tiny knots of gas, composed of sulfur, oxygen, argon, and neon from the star itself, are only detectable thanks to NIRCam's exquisite resolution, and give researchers a hint at how the dying star shattered like glass when it exploded. The outskirts of the main inner shell look like smoke from a campfire. This marks where ejected material from the exploded star is ramming into surrounding circumstellar material. Researchers have concluded that this white color is light from synchrotron radiation, which is generated by charged particles traveling at extremely high speeds and spiraling around magnetic field lines. There are also several light echoes visible in this image, most notably in the bottom right corner. This is where light from the star's long-ago explosion is reached, and is warming distant dust, which glows as it cools down. A delicate tracery of dust and bright star clusters threads across this image. The bright tendrils of gas and stars belong to the barred spiral galaxy NGC 5068, whose bright central bar is visible in the upper left of this image. NGC 5068 lies around 17 million light-years from Earth in the constellation Virgo. This portrait of NGC 5068 is part of a campaign to create an astronomical treasure trove, a repository of observations of star formation in nearby galaxies. Previous gems from this collection can be seen here and here. These observations are particularly valuable to astronomers for two reasons. The first is because star formation underpins so many fields in astronomy, from the physics of the tenuous plasma that lies between stars to the evolution of entire galaxies. By observing the formation of stars in nearby galaxies, astronomers hope to kickstart major scientific advances with some of the first available data from Webb. The second reason is that Webb's observations build on other studies using telescopes, including the NASA/ESA Hubble Space Telescope and some of the world's most capable ground-based observatories. Webb collected images of 19 nearby star-forming galaxies, which astronomers could then combine with catalogs from Hubble of 10,000 star clusters. The peculiar galaxy NGC 3256 dominates this image. This Milky Way-sized galaxy lies about 120 million light-years away in the constellation Vela, and is a denizen of the Hydra Centaurus supercluster. NGC 3256 may seem peaceful, a swirl of tightly entwined spiral arms set in a hazy cloud of light, but this image shows the aftermath of an ancient cosmic clash. This distorted galaxy is the wreckage of a head-on collision between two equally massive spiral galaxies, which astronomers estimate to have met around 500 million years ago. The tumultuous past of NGC 3256 is captured in the long tendrils of shining dust and stars which extend outwards from the main body of the galaxy. The striking red and orange regions spread across the galaxy contain young stars created in the merger that are irradiating small dust grains, which then emit infrared light that is captured in astonishing detail by Webb's instruments. Further out, there are extended tidal features which are mostly stars pulled out of the galaxies when they collided. If you were asked to picture a galaxy collision, you might picture stars careening into one another with catastrophically explosive results. In reality, the spaces between the stars in a galaxy are vast. The first anniversary image from the NASA James Webb Space Telescope displays star birth like it's never been seen before, full of detailed, impressionistic texture. The subject is the Rho-Ophiuchi cloud complex, the closest star-forming region to Earth. It is a relatively small, quiet stellar nursery, but you'd never know it from Webb's chaotic close-up. Jets bursting from young stars crisscross the image, impacting the surrounding interstellar gas and lighting up molecular hydrogen, shown in red. Some stars display the telltale shadow of a circumstellar disk, the makings of future planetary systems. The young stars at the center of many of these disks are similar in mass to the Sun or smaller. The heftiest in this image is the star S1, which appears amid a glowing cave it is carving out with its stellar winds in the lower half of the image. The lighter colored gas surrounding S1 consists of polycyclic aromatic hydrocarbons, a family of carbon-based molecules that are among the most common compounds found in space. NGC 346 is a young open cluster of stars with associated nebula located in the Small Magellanic Cloud, SMC, that appears in the southern constellation of Tucana. It was discovered August 1, 1826 by Scottish astronomer James Dunlop. Dreyer described it as bright, large, very irregular figure, much brighter middle similar to double star, modeled but not resolved. On the outskirts of the cluster is the multiple star system HD 5980, one of the brightest stars in the SMC. Description: this cluster is located near the center of the brightest H2 region in the SMC, designated N66. This is positioned in the northeast section of the galactic bar. Stellar surveys have identified 230 massive OB stars in the direction of this cluster. 33 of the cluster members are O-type stars, with 11 of type 6.5 or earlier. The inner 15 PC radius of the cluster appears centrally condensed, while the area outside that volume is more dispersed. The youngest cluster members near the center have ages of less than 2 million years, and observations suggest the cluster is still engaged in high-mass star formation. The James Webb Space Telescope dissected the Crab Nebula structure, aiding astronomers as they continue to evaluate leading theories about the supernova remnant's origins. With the data collected by Webb's near-infrared camera and mid-infrared instrument, a team of scientists were able to closely inspect some of the Crab Nebula's major components. For the first time ever, astronomers mapped the warm dust emission throughout the supernova remnant, represented here as fluffy magenta material. The dust grains form a cage-like structure that is most apparent toward the lower left and upper right portions of the remnant. Filaments of dust are also threaded throughout the crab's interior and sometimes coincide with regions of doubly ionized sulfur, sulfur-3, colored in green. Yellow-white mottled filaments, which form large loop-like structures around the supernova remnant center, represent areas where dust and doubly ionized sulfur overlap. The dust's cage-like structure helps constrain some, but not all of the ghostly synchrotron emission represented in blue. The emission resembles wisps of smoke, most notable toward the crab's center. sharpest infrared images to date of one of the most distinctive objects in our skies, the Horsehead Nebula. These observations show a part of the iconic nebula in a whole new light, capturing its complexity with unprecedented spatial resolution. Webb's new images show part of the sky in the constellation Orion, the Hunter, in the western side of the Orion B molecular cloud. Rising from turbulent waves of dust and gas is the Horsehead Nebula, otherwise known as Barnard 33, which resides roughly 1,300 light-years away. The nebula formed from a collapsing interstellar cloud of material and glows because it is illuminated by a nearby hot star. The gas clouds surrounding the Horsehead have already dissipated, but the jutting pillar is made of thick clumps of material that is harder to erode. Astronomers estimate that the Horsehead has about 5 million years left before it too disintegrates. Webb's new view focuses on the illuminated edge of the top of the nebula's distinctive dust and gas structure. The Horsehead Nebula is a well-known photon-dominated region. In such a region, ultraviolet light from young, massive stars creates a mostly neutral, warm area of gas and dust between the fully ionized gas surrounding the massive stars and the clouds in which they are born. This ultraviolet radiation strongly influences the gas chemistry of these regions and acts as the most important source of heat. The distorted spiral galaxy at the center, the Penguin, and the compact elliptical galaxy at the left, the Egg, are locked in an active embrace. The pair, known jointly as ARP-142, made their first pass between 25 and 75 million years ago, causing fireworks or new star formation in the Penguin. In the most extreme cases, mergers can cause galaxies to form thousands of new stars per year for a few million years. For the Penguin, research has shown that about 100 to 200 stars have formed per year. By comparison, our Milky Way galaxy, which is not interacting with a galaxy of the same size, forms roughly 6 to 7 new stars per year. This gravitational shimmy also remade the Penguin's appearance. Its coiled spiral arms unwound, and gas and dust were pulled in an array of directions, like it was releasing confetti. It is rare for individual stars to collide when galaxies interact. Space is vast, but the galaxies mingling disrupts their stars' orbits. Today, the Penguin's galactic center looks like an eye set within a head, and the galaxy has prominent star trails that take the shape of a beak, backbone, and fanned-out tail. A faint but prominent dust lane extends from its beak down to its tail. Despite the Penguin appearing far larger than the Egg, these galaxies have approximately the same mass. This is one reason why the smaller-looking Egg hasn't yet merged with the Penguin. If one was less massive, it may have merged earlier. The oval Egg is filled with old stars and little gas and dust, which is why it isn't sending out streamers or tidal tails of its own and instead has maintained a compact oval shape. If you look closely, the Egg has 4 prominent diffraction spikes. The galaxy stars are so concentrated that it gleams. Near the outskirts of the Small Magellanic Cloud, a satellite galaxy roughly 200,000 light-years from Earth, lies the young star cluster NGC 602, which is featured in this new image from the NASA James Webb Space Telescope. This image includes data from Webb's NIRCam, near-infrared camera, and MIRI, mid-infrared instrument. The local environment of this cluster is a close analog of what existed in the early universe, with very low abundances of elements heavier than hydrogen and helium. The existence of dark clouds of dense dust and the fact that the cluster is rich in ionized gas also suggests the presence of ongoing star formation processes. This cluster provides a valuable opportunity to examine star formation scenarios under dramatically different conditions from those in the solar neighborhood. An international team of astronomers, including Peter Zeidler, Elena Sabai, and Antonella Noda, used Webb to observe NGC 602 and detected candidates for the first young brown dwarfs outside our Milky Way. The NASA James Webb Space Telescope recently imaged the Sombrero Galaxy with its MIRI mid-infrared instrument, resolving the clumpy nature of the dust along the galaxy's outer ring. The mid-infrared light highlights the gas and dust that are part of star formation taking place among the Sombrero Galaxy's outer disk. The rings of the Sombrero Galaxy produce less than 1 solar mass of stars per year, in comparison to the Milky Way's roughly 2 solar masses a year. It's not a particular hotbed of star formation. The Sombrero Galaxy is around 30 million light-years from Earth in the constellation Virgo. This image of protostar Lens 483, L483, captured by the NASA/ESA/CSA James Webb Space Telescope's NIRCam near-infrared camera, shows compass arrows, scale bar, and color key for reference. The north and east compass arrows show the orientation of the image on the sky. Note that the relationship between north and east on the sky, as seen from below, is flipped relative to direction arrows on a map of the ground, as seen from above. The scale bar is labeled in light years, which is the distance that light travels in 1 Earth year. It takes 0.1 years for light to travel a distance equal to the length of the scale bar. 1 light year is equal to 9.46 trillion kilometers. This image shows invisible near-infrared wavelengths of light that have been translated into visible light colors. The color key shows which NIRCam filters were used when collecting the light. The color of each filter name is the visible light color used to represent the infrared light that passes through that filter. Herbig-Haro 4950, an outflow from a nearby still-forming star, in high-resolution near and mid-infrared light with the NIRCam and MIRI instruments. The intricate features of the outflow, represented in reddish-orange color, provide detailed clues about how young stars form and how their jet activity affects the environment around them. A chance alignment in this direction of the sky provides a beautiful juxtaposition of this nearby Herbig-Haro object, located within our Milky Way, with a more distant face-on spiral galaxy in the background. Protostars are young stars in the process of formation that generally launch narrow jets of material. These jets move through the surrounding environment, in some cases extending to large distances away from the protostar. Like the water wake generated by a speeding boat, the arcs in this image are created by the fast-moving jet slamming into surrounding dust and gas. This ambient material is compressed and heats up, then cools by emitting light at visible and infrared wavelengths. In particular, the infrared light captured here by Webb highlights molecular hydrogen and carbon monoxide. The galaxy that appears by happenstance at the tip of Herbig-Haro 4950 is a much more distant spiral galaxy. It has a prominent central bulge represented in blue that shows the location of older stars. celebrate the James Webb Space Telescope's third year of highly productive science, astronomers use the telescope to scratch beyond the surface of the Cat's Paw Nebula, NGC 6334, a massive, local star-forming region. This area is of great interest to scientists, having been subject to previous study by NASA's Hubble and retired Spitzer space telescopes, as they seek to understand the multiple steps required for a turbulent molecular cloud to transition to stars. With its near-infrared capabilities and sharp resolution, the telescope clawed back a portion of a singular toe bean, revealing a subset of mini-toe bean reminiscent structures composed of gas, dust, and young stars. Webb's view reveals a chaotic scene still in development. Massive young stars are carving away at nearby gas and dust, while their bright starlight is producing a bright nebulous glow represented in blue. This is only a chapter in the region's larger story. The disruptive young stars, with their relatively short lifespans and luminosity, will eventually quench the local star formation process. The Cat's Paw Nebula is located approximately 4,000 light-years away in the constellation Scorpius. This view of the Butterfly Nebula, NGC 6302, comes from the NASA Hubble Space Telescope. In the optical wavelengths shown here, the wings of the Butterfly Nebula appear clumpy and nearly opaque, blocking most of the background stars from view. The orange color that suffuses the wings comes from ionized nitrogen and hydrogen, while the red accents come from ionized sulfur. Blue comes from hydrogen atoms. This Hubble image highlights the Butterfly Nebula's bipolar shape, showing how its two lobes spread in opposite directions, forming the wings of the butterfly. A dark band of dusty gas poses as the butterfly's body. This band is actually a donut-shaped torus that's being viewed from the side, hiding the nebula's central star, the ancient core of a sun-like star that energizes the nebula and causes it to glow. The dusty donut may be responsible for the nebula's insectoid shape by preventing gas from flowing outward from the star equally in all directions.
This sparkling scene of star birth was captured by the James Webb Space Telescope. What appears to be a craggy, starlit mountaintop kissed by wispy clouds is actually a cosmic dustscape being eaten away by the blistering winds and radiation of nearby, massive, infant stars. Called Pismis 24, this young star cluster resides in the core of the nearby Lobster Nebula, approximately 5,500 light-years from Earth in the constellation Scorpius. Home to a vibrant stellar nursery and one of the closest sites of massive star birth, Pismis 24 provides rare insight into large and massive stars. This region is one of the best places to explore the properties of hot young stars and how they evolve. James Webb Space Telescope recently imaged an extremely large stellar jet at the outskirts of our Milky Way galaxy in the protocluster 2 to 284 Schillings. This Herbig-Haro HH object, jets of plasma shooting out from newly formed stars, is 8 light-years across. This is about double the distance from our Sun to its closest neighboring star system, Alpha Centauri. Its detection provides evidence that HH jets scale with the mass of their parent stars. The more massive the stellar engine driving the plasma, the larger the resulting jet. Thanks for watching. This wasn't about accuracy, it was about perception. Tell me how it felt.